Hello everyone. In the last lecture, we discussed the alpha decay and we observed that alpha decay is seen in the heavy nuclei, particularly the masses more than 200. But of course, up to 150 to 200 also alpha decay has been seen with very, very long half-lives. And then we also discussed that the half-lives for alpha decay would be explained by considering the barrier penetration formula. And also we discussed the systematics of alpha decay among the isotopes and the isobars of a particular element or isobaric chain. Today we will discuss the beta decay. As all of you know, that beta decay happens along a isobaric chain because the mass number does not change in the beta decay. Beta decay could be beta minus decay, wherein the atomic number increases by 1, or it could be beta plus decay, wherein the atomic number decreases by 1. So I have just given the schematic for beta decay. In beta minus decay, the atomic number increases by 1, and along with that, a beta minus, which is an electron, and an antineutron is emitted. For example, sodium 24 emits a beta minus to give you sodium magnesium 24. In beta plus decay, the atomic number decreases by 1, emitting a positron and a neutrino. And this reaction has got a threshold of 1.02 MeV. So why this condition has come? Why is there a threshold for beta plus decay, and why there is no threshold for beta minus decay? So as you can see here, that when the atomic number increases from Z to Z plus 1 by beta minus decay, there is one extra, so there is extra electron in the, so for example, you take sodium going to magnesium. Now this sodium, so when it comes to magnesium, it is actually one electron more, but there is no electron gain, so it will pick up electron. It will become actually positively charged. When sodium converts to magnesium, it will be positively charged. It can easily pick up an electron from the surrounding. So one electron was emitted by sodium 24 and magnesium picks up an electron. So in terms of electron, there is no loss or gain. But in case of beta plus decay, when the atomic number decreases by 1, for example, phosphorus goes to silicon, phosphorus 30 goes to silicon 30. So from 15 it becomes 14. Then when a electron, see here it is what is happening, a positron is coming out, and there is a, so this atomic number has decreased. So there is one extra electron, there is one electron is actually gone. So, it is one electron less than the parent isotope. Because of that, the atom loses an electron from the atomic shells. So instead of, so because of that, there is a pair, a positron is going out and electron from the atomic cells is going out. So because of this condition, the mass difference between the parent and daughter has to be more than the rest mass of a pair of electron positron, that is 1.02 MeV. I hope it is clear. In beta plus decay, since the atomic number has decreased, the electron, the positron is anyway emitted, but the electron which is excess now in silicon 30, that electron also will be emitted, and so the mass difference between the parent and daughter has to be more than or equal to the rest mass of a pair of electron positron, that is 1.02 MeV. So whenever the Q beta value is more than 1.02, then only the beta plus decay is possible. Otherwise, beta plus decay not possible. And in such situation, when Q beta is less than 1.02 MeV, electron capture is the mode of decay. So electron capture competes with beta plus decay when Q beta is less than 1.02 MeV. Just to give an example, beryllium 7. So it is electron capture. What does it mean? The nucleus captures the electron on the atomic orbitals. So it could be K electron or L electron depending upon the Q value for the reaction. So electron is captured by the nucleus and you have here lithium 7 plus neutrino. So this is in this process there are no particle is emitted, but when the electron is captured by the beryllium, lithium 7 will have a hole in the K shell and there will be emission of gamma X-rays from the atoms. So electron capture is always accompanied by emission of X-rays and also the OZ electrons. So these particles that are emitted in the beta decay, it could be electron or positron and also the neutrino and antineutrinos. Let us first discuss the energetics of the beta decay. As we have seen previously that beta decay occurs along the isobaric chain, say particular A, for example, it is odd A, then the lower Z like this and tin, antimony, tellurium, they are undergoing beta minus decay and the higher Zs are undergoing beta plus decay to stabilize at the most stable isobar. And as you can see here, the Q beta values are decreasing from both sides. So as the whatever nucleus is away from the stability has got a higher Q value. One of the important observations of beta decay was that beta spectrum is continuous. Just I have given an example here. The phosphorus 32 has a spin of 1 plus undergoing beta minus emission to sulfur 32, which has a spin of 0 plus. So this gamma decay, the beta decay taking place between two discrete states, ground state of phosphorus 32 to that of the sulfur 32. But then if you see the beta spectrum, what is this? Energy of electron versus the number of electron, or dN by dE. The beta spectrum is continuous. The blue one is beta minus and the red one is the beta plus. So beta minus or beta plus have a continuous spectrum. So this cannot be explained simply if you consider the decay of a state of 1 plus 2, another state, both of them are discrete. So apparently there looks to be a violation of conservation of mass and energy. How to explain this mass, the continuous spectrum beta spectrum we will see shortly. Another violation that appears to be here is the angular momentum conservation. You see here, phosphorus 32 is 1 plus, sulfur 32 is 0. If only electron was emitted, or then electron spin is half. So 1 plus minus half can be half or 3 by 2, but the dot product spin is 0. So again, the initial spin and final spin are not matching, and apparently there is a violation of the conservation of angular momentum. So this puzzle was actually solved by Wolfgang Pauli in 1930 when he proposed the neutrino hypothesis. You see, it was a hypothesis. Wolfgang Pauli proposed that there has to be one more particle emitted along with the beta particle in beta decay. And that particle he named as neutrino. So this is that another particle is accompanied beta particle. So two particles are emitted along with the residue nucleus that is formed. And the properties that Pauli predicted, it has to have a spin of half, no charge and no mass. So once you include one more particle neutrino having a spin half, no charge and no mass, then you can explain the conservation of mass and energy as well as that of the environment. So you can see here, when you have another particle, so there are three particles now. So a neutron is getting converted into a positron, plus electron, for proton, electron minus plus a neutrino. And so the Q beta of this reaction is shared among the three particles. And when the Q is shared among three particles, there can be infinite solutions. Therefore, the energy of electron and neutrino can be very continuously. So in this particular one, when the energy of electron is very high, then energy of neutrino will be low. When energy of electron is very low, energy of neutrino will be high. So that is how you can explain the continuous spectrum of beta. Similarly, the angular momentum also can be explained now. So you have the phosphorus 32 1 plus charge state, an electron goes out, and a neutrino also is emitted, both having spin half, spin half. So the angular momenta can couple in a way L plus minus half, and so there is a combination of L and S1, S2. Here S1, S2 electron and neutrino can give you zero spin. For example, if you have 1 minus half minus 1 half can be 0. So it is now possible to explain the conservation of angular momentum by spin half neutrino, and it is also possible to explain the continuous nature of the beta spectrum. So this, in fact, this neutrino was discovered in 1956. You can see here. And the reaction was that in the reactors, there are a lot of neutrino. When there is a fission, there is a neutrino emitted, beta decay. There is a hydrogen. So the neutrinos interact with the hydrogen to give you a neutron and a positron and a triple coincidence. So you detect the neutrino in a detector, neutron in neutron detector, and the positron will annihilate, give you two 511 keV gamma ray. So the triple coincidence between one neutron and two 511 keV gamma ray is a unambiguous proof of the existence of neutrino. So that is how the neutrino was discovered after almost 25 years of its prediction by Pauli. So we can explain the energetics. Now let us see how to explain the decay constant. So that the theory of the beta decay was in fact given by Enrico Fermi in 1934. And the first question it comes to mind is whether this electron that is emitted, it comes from nucleus, or how it comes. So that is the question. And we will see later on that actually it is not present in the nucleus. Electron is not present in the nucleus, but it is generated whenever there is a weak interaction. We will see that. So let us see why it is not present in the nucleus, because wavelength of the electron, if you have 1 MeV electron coming out in beta decay, and what is the wavelength? Lambda is given by h upon p, momentum, the de Broglie wavelength, or p can be written as root 2 me, with mass and energy. And if you substitute the value of the Planck's constant in joule second, and then the mass of the electron, and then the conversion factor for joule to MeV, it comes to 10 to the power minus 13 meters. So the wavelength of the electron having energy of about beta particles is much larger than the dimensions of the nucleus. Therefore, the hypothesis that if electron is present in nucleus is not possible. So essentially, the beta particle is created during the conversion of a neutron into a proton, or a beta plus is created in a bound proton, because the proton mass is less than that of neutron. So proton cannot decay into neutron, a free proton. But a bound proton in the nucleus can be converted into a neutron by emission of a beta plus. So these are the expressions give you how the conversion between neutron proton happening in the beta decay. So these particles, electron and positron, are created when the one nucleon is converted into another in this process. Now to calculate the decay constant, we will go a little bit into the more details, though I will not able to go to complete theory, complete derivations of the expression for the decay constant, but I'll give you a flavor by considering what are the major factors that Fermi took in the determining the lambda for the beta decay. So Fermi golden rule for any transition is given by this kind of expression. Here it is only for the beta decay. That is the probability that an electron is emitted with momentum between Pe and Pe plus dPe. That means Pe to a small increment in a Pe plus delta E, delta Pe. What is the probability that electron is emitted? And corresponding to that probability, there is a electron, a neutrino also emitted. So when there is a dPe, there will be dP nu also. So NP dPe is given by Fermi golden rule 4 pi square by h. The probability of finding electron at the nucleus psi E, psi nu, probability of finding the neutrino at the nucleus. This is the matrix element between initial and final state for beta decay. G is the G factor which Fermi introduced to characterize the weak interaction between the three particles, nucleus, electron, and the neutrino. And in fact, this G is analogous to electronic charge in electromagnetic interaction. So it is essentially a particle of weak interaction. And then this is the density, statistical factor, which is density of states. So when, for example, a particular isotope is decaying by beta, so it will be populating some states. So what are the density of states in the nucleus? Suppose it emits gamma ray. So there is the density of states dN by dE. So when the electron is emitted and along with that neutrino is also emitted, then the density of states in the residual nucleus will be given by dN by dE0. And E0, the total energy of kinetic energy of total kinetic energy is equal to energy of electron plus energy of the neutrino. So E0 is shared in an infinite number of ways between electron and neutrino. So let us see how we can derive the final expression for the decay constant. So a little bit more details. The dN, the density factor, is nothing but the dNe into dN nu, density for the electron and neutrino, and it is, you can see the phase space and the momentum space for the electron and neutrino, 4 pi p square dp by h cube. These are the momentum space for electron and neutrino. So it is calculated to be 16 pi square by h cube into E nu square by c square. So you can say P equal to E by c for neutrino and dE0 by c. And so dE0, because E nu is E0 minus EE. So since EE is constant, you can say dE nu is dE0. So you actually try to eliminate the term corresponding to the momentum and energy of neutrino, because what we are observing is the electron. So P nu can be eliminated using P nu equal to E nu by c, and so that is equal to E0 minus EE by c, and accordingly then dP nu will be dE0 by c. From here dP nu will be dE0 by c. So final expression will be dN by d0 will be the term, momentum space term, then PE square, E0 minus EE square into dP. So we have now the terms in energy and momentum of electron. And now we can make a small substitution, that is called in the relativistic domain, you can write the relative momentum in terms of the momentum of electron and m0c, relativistic momentum of electron. So PE upon m0c. Similarly, the energy can be written as kinetic energy of electron upon the S mass energy. So it is the relativistic energy W. So these two terms, eta and W, we introduce to get this simplified version. dN by dE0, which is the term corresponding to this 16 pi square m05 C4 upon H6 into W square minus 1, W0 minus W square into W dW, where W is nothing but the relative energy and eta is the relative momentum. And you can also find out that W square is nothing but 1 plus eta square, or eta square is W square minus 1. So finally, you can see this expression. Actually, the density term just explains the shape of the beta spectrum. When W becomes 1, that means eta equal to 0. So that corresponds to the 0 momentum of electron. When W becomes a W0, then this term becomes 0. So at both ends, first end 0 energy term end W equal to 1, and the highest energy term W0 equal to W. So the bell-shaped spectrum of beta can be explained by this Fermi decay theory. But the observation is that, you see, the bell shape is observed for beta plus, but for beta minus, there is at low energy there is a rise. So more electrons of low energy are observed than beta plus. So this difference is there. So this is explained by a Coulomb correction factor. That means when the electron or positron is coming out of the nucleus, electron is attracted by the nucleus, whereas positron is repelled by the nucleus. In simple terms to explain. So there are more high energy positrons than electrons. There are more low energy electrons than positrons. That's why the electron spectrum has a lower energy component more than the positron. So this Coulomb correction factor was given by Fermi. It depends upon the atomic number of the nucleus and the energy. W is the relative energy, and it is given by 2 pi y upon 1 minus e raised to minus 2 pi y, where y is Ze square by hv, where Z is the atomic number of the residual nucleus and v is the velocity of beta particle at infinity. And this term y is actually positive for electrons and negative for positrons. And if you substitute this value, this plus minus y plus minus Ze square by hv in the factor here, then we can explain the shape of the beta minus spectrum. Beta minus spectrum is more having high low energy component. Beta plus spectrum has got high energy component. So that is how the Coulomb correction term can explain the shape of the beta minus and beta plus. The Fermi theory in fact got a boost when it was successfully validated by Curie plot. So Curie in fact came out with an excellent idea of plotting what is called as this factor. Let us see what is this factor. So again when I am saying momenta, it is the momentum, relative momentum eta. So n eta d eta proportional to fz, Coulomb correction factor, eta square w0 minus w. You can write it from the previous expressions, and then you can rearrange this equation that n eta upon the f factor to the power half equal to a constant into w0 minus w. So actually it has to be square term here. So this term now, if you plot this left hand side against w, then you get this term. So IW is nothing but n eta. You can write in terms of w or eta. W is related. W square is equal to 1 plus eta square upon the Coulomb factor eta square to the power half was found to follow a straight line with a negative slope because of this negative term. And very nicely these plots, Curie plots in fact, were used to identify if there is a monoenergetic, there is a single beta or there are multiple beta particles. So like if there are more than one beta group, then you have these two linear paths. If there are more than two, you have three linear paths and so on. So the Curie plot was very handy when the mass spectrometers were utilized to determine the electron spectrum in momentum space. Mass spectra will resolve them as per their momentum. And when you plot the data, this particular expression IW upon FZW, then you find that each beta group followed a straight line with the slope that you can find from this equation. So this was the success of Curie plot that validated the Fermi theory of beta decay. Now let us see how to compare the half-lives for beta decay. So again the same expression I am writing again in more details. NWDW is the term which came from the momentum space, the G factor, the transition matrix square, Coulomb correction factor, and the W energy factors. Now the decay constant essentially is as we discussed previously, the decay constant lambda is nothing but the probability of decay per unit time. Probability of decay of an atom per unit time. So if you integrate this equation over from W equal to 1, that means energy from 0 to highest energy, then you integrate this NW dW, this expression. So you get, it can be final expression I am giving K, a constant term, MFIF square, the transition matrix square, FZ comma W0, and this you can lambda you can mention as 0.693 or ln2 upon T half. So T half into F is called Ft. In fact, it is very popularly called as Ft. Then that is Ft is proportional to constant upon MF square, where M is the matrix element for transition. So you can see here Ft is inversely proportional to MIF square. Smaller the value of log Ft, greater the value of MIF square. Essentially, it means that if a transition is allowed, it will have higher value of MIF. So lower value of log Ft is an indication of a allowedness of it. So for allowed transitions, log Ft is varying from 3 and it goes on to higher values. We will see it very soon. So the selection rules for beta decay are, in fact, there were two selection rules, one by Fermi, because depending upon the spins of electron and neutrino, whether they are perpendicular to each other or parallel to each other, whether they are parallel or anti-parallel. So if electron and in the Fermi selection rule, electron and neutrino are emitted anti-parallel to each other, so the spin component is 0. Whereas in the Gamow-Taylor selection rule, electron and neutrino are emitted with parallel spin, so the spin factor is 1. So Fermi selection rule says II equal to IF plus L. L is the angular momentum carried away by the electron, and so S becomes, because S is 0. But Gamow-Taylor selection rule says that II equal to IF plus L plus 1. 1 is due to the spins of electron and neutrino, which add up to 1. For allowed transitions, we say L equal to 0 and there is no change in the parity because this is the S wave alpha particle. So we can say L plus S equal to II minus IF to II plus IF, where II and IF are the spins of the parent and daughter isotopes. Delta pi, the change in parity, is given by -1 to the power n. These are the selection rules. The super allowed transitions occur between the pairs of mirror nuclei. You can see from neutron to proton, or tritium to helium-3, or fluorine-17 to fluorine-17 to oxygen-17. You can see here that the orbitals of proton and neutron in the two nuclei are exactly same. As a result of that, the delta I is 0, delta L is 0, and delta pi is 0. That means there is no change in parity, and the log of T values are of the order of 3. Whereas in the case of allowed transitions, the delta I is 0, but the proton and neutron need not necessarily occupy the same orbital. Therefore, delta I is 0, L equal to 0, and no change in parity, but the log of T values are higher than 3 in the range of 4 to 7. First forbidden, now you can see delta I 0, 1, 2, L value 1, 1, 1, and there is a change in parity. So log of T values are higher. And second forbidden, again, delta I is 2, L is 2, no change in parity, 10 to 13 log of T. Third forbidden, and so on. So as you go to higher and higher forbiddenness, there is a rise in the L value. Just to give an example of this decay, sodium 24 having spin state 4 plus decays to magnesium 24, and you see the ground to ground transition is forbidden because it is delta I equal to 4. Whereas the 100% transition goes to 4 plus state. The 4 plus is allowed transition. Delta I is 0, delta pi is no change in parity. 4 to 2, see this second forbidden transition, delta I is 2 and delta pi is no change in parity, whereas there is no ground to ground transition. So that is how we can explain type of transition. And lastly, just to, before I conclude, just I was telling about the how electron and neutrino are coming out. So from the quark structure of nucleons, a neutron is UDD, 1 up quark and 2 d quark. A proton is UUD, 2 up quark and 1 d quark. And so conversion of a d quark into u quark happens during beta minus decay. So this is actually nicely explained by this Feynman diagram, A neutron is converted into a proton. In the process, a double boson is emitted, and then this double boson decays to a electron and a antineutrino. So that is how, in fact, the advanced theory of beta decay is in terms of the weak interaction, whereby the neutron, when the neutron is converted into positive proton, then a double boson is emitted, and in the process, double boson breaks into electron and a neutrino. And the forward-backward asymmetry of beta particles, in fact, was observed. That explains that in the beta decay or in the weak interactions, parity is not concerned. So these bosons, W bosons and Z bosons, in fact, they are actually the particles that are mediating the weak interactions in beta decay. And you can see the masses of these particles, they are very high, of the order of GeV. So this is, in fact, ultimately all these interactions, beta decay, weak interactions are explained in terms of the weak interactions wherein the W bosons or the Z bosons are involved in the process. So I will stop here, and next I will take the gamma decay. Thank you very much.